right, thank you, Rolf, for that great overview and thoughtful welcome. So as you've heard, education is a key theme of Connect, and so we're gonna take the next 30 minutes to provide an introduction to carbon management. So I'm pleased to invite Brent Hagy and Meghan Kenny up to the stage, and we'll also be joined virtually by Sallie Greenberg, who has a pre-recorded video for us. Each of our speakers will be presenting on a portion of the carbon management value chain. So first up, we have a presentation on carbon transport and storage by Dr. Sallie Greenberg. Sallie is a scientist, strategic advisor, and engagement specialist with over 30 years of experience in the environmental and energy geosciences. Her work on diverse carbon capture and storage projects, including her time as a principal research scientist on the Illinois Basin Decatur project, has made her a world-renowned and sought-after consultant and invited speaker for a variety of organizations working at the intersection of science, sustainability, and society. Please enjoy Sallie's remarks.
Good morning. Thank you so much for the opportunity to talk to you today about the carbon management system and the technologies that are combined uniquely to create a system where we can capture, transport, utilize, or store carbon dioxide. The focus of my remarks today are primarily going to be about carbon storage, but I like to think about carbon management as a full system, and you're going to hear a great deal more about utilization and capture from some of the other people in this session, but I thought I would give the overall picture. So what happens in carbon management is that we're capturing carbon dioxide from a point source or directly removing it from the atmosphere. We're transporting that carbon dioxide via pipeline, ship, or truck to a location where it can either be utilized for something or stored for permanent geologic storage. And that entire system is depicted in this figure. Carbon capture happens from different emission sources, either chemically or physically using solvents membranes. And as I mentioned, there's two main methods to capture carbon dioxide in the atmosphere. One is mitigation, which is to capture it before it goes into the atmosphere, and one is removal, where you're directly removing it from the atmosphere. Utilization is using that carbon dioxide in some other material to create chemicals, grow algae for biofuels or animal feed, and there's a variety of different ways that you can utilize carbon dioxide by making it into a viable feedstock for other products. Transportation is simply moving carbon dioxide from one location to another. And then we get to carbon storage. So carbon storage is the physical, permanent, deep underground storage of carbon dioxide in geologic formations. And so what do I actually mean by that? So the Earth stores water, saline water, or brine, which is super salty, maybe 6 or 7 times saltier than the ocean, oil and natural gas in pore spaces in rock units beneath the surface. So this picture is what we call a photomicrograph. It's essentially a very thin slice of a rock, and everything that you see in blue is a pore space, or a space where rocks don't touch but are filled with some sort of fluid. The principle of geologic storage is that we're harnessing the Earth's natural trapping system to store carbon dioxide. So we have what we call sinks and seals. And so a rock that has a set of pore spaces, open spaces in it, is a place where you could store liquid carbon dioxide in the salty brine that's in place. We look for rocks that have a specific property called porosity and permeability. So porosity is the volume of pore space that exists in a rock formation, and the permeability is the connectedness of those pore spaces. So for example, something like a Swiss cheese, which has a lot of holes, but they aren't very well connected, might have high porosity but low permeability, which does not necessarily make it ideal for carbon storage. On the other hand, if you take an Alpine lace cheese, which has lots of little holes that are pretty well connected, that is a porous and permeable uh, rock type, if it's not cheese, that allows you to store carbon dioxide. Because essentially what you're doing is you are capturing carbon dioxide from a source, you're compressing that, purifying it, removing any water, and creating a liquid-like carbon dioxide that gets transported to a wellhead and then gets injected and stored in a specific sandstone or other porous rock formation deep in the surface. And then you keep that carbon dioxide in place and ensure that it doesn't leak upward by having a different rock type on top of it, which is very, very low permeability, such as a shale. And so what you have essentially is this package of rocks where one acts as a storage unit and the other acts as a seal. So we look at different properties when we're looking at characterizing rock formations. So the injectivity, can you put carbon dioxide into the rock formation? Capacity, how much carbon dioxide can you put into the rock formation? And containment, do you have an appropriate seal? Do you have a thick seal that allows you to keep that carbon dioxide in the rock formation? The other thing that's incredibly important and vital to carbon storage is site characterization and then subsequent monitoring. So when you are determining where to store carbon dioxide, you're looking for the rock types and the rock properties that we just talked about. But you're also looking for what do you know about the geologic complex that allows you to ensure and build a system that is safe for storage. So what we do ahead of time is we characterize the site. We do essentially seismic, we take seismic studies, which are sort of like taking a sonogram of the Earth, where we send energy waves down and reflect back and record, and we get a picture of what the Earth looks like in the subsurface where we're interested in. We drill wells, we take rock samples, we do environmental testing and characterization of the surface. We do all of that before we apply for permits for the storage of carbon dioxide, and I'll talk just a little bit about that in a minute. And so we pre-characterize, and then once you build your infrastructure, your safe wells that use carbon dioxide resistant materials, then you have a monitoring system that you utilize in place. So you've taken you've characterized the environment beforehand, you continue to monitor during injection of carbon dioxide, and then you're required by federal law to monitor a site for decades afterwards, on the order of 50 to 100 years, depending on where you are. And you do that through a variety of different techniques at a variety of different locations. Some happen at the surface and in the soil, some happen in the shallow groundwater, and some of those monitoring technologies happen very deep in the subsurface in the location where the carbon dioxide is being stored. So the safety really comes in part from this whole characterization and sequence of monitoring and information gathering that happened before, during, and after the storage of carbon dioxide, but they are regulated by federal law through the U.S. Environmental Protection Agency's Underground Injection Control Program, which is in place as a function of the Safe Drinking Water Act. And so there's a specific class of well for the storage of carbon dioxide. You have to apply either to the federal regional office, depending on your location, or if your state has primacy for class 6, and you have to set up a rigorous testing system and reporting system that shows that you are continuing to operate a safe and viable carbon dioxide system. With that, I will close my remarks. I think that you're in for a very interesting set of talks and sessions today. And I want to encourage any of you to seek more information and just emphasize how important it is to understand the factual basis of the technology and the amount of testing and work that has been happening in this space for about the last 30 years, which also builds on a century worth of exploration in the deep subsurface. So I wish you a very successful conference and look forward to hearing from you if you want to reach out and contact me. Thank you.
All right. Thank you, Sallie, wherever you are. Up next, we have a presentation on carbon utilization and the circular economy by Brent Hagy, who's the General Counsel at CarbonFree. CarbonFree has developed patented technologies that capture CO2 from point source emitters and transform them into carbon negative chemicals. We're lucky to have Brent, who has over 20 years of experience as in-house counsel with public and private companies, with us to share more. Welcome, Brent.
Thank you very much. It's good to be with you this morning, and I would really enjoy this opportunity to talk to you about both circular economy and carbon utilization. Next. So first of all, just to talk about CarbonFree just for a moment, our mission is to help the world's transition to net zero, and specifically by utilizing CO2 from hard-to-abate industrial emissions and enabling the circular economy. And it is really those two things that I want to talk with you about today, utilization and circular economy. And so to do that, what I'd like to do is start by kind of defining carbon utilization and circular economy for you. And then next, really talk about our technology at CarbonFree as an example of utilization and as an example of enabling the circular economy, to just give you a little deeper understanding of the possible. Next, please. So our first speaker actually defined carbon utilization for us, but I would do it very simply and say, you know, what carbon utilization is all about is converting carbon dioxide into valuable products. And there are a number of examples of technologies that have either been developed or are under development today for the utilization of carbon dioxide emissions. And these can be from everything from aggregates and cement to fertilizer to sustainable fuels and even commodity chemicals. Now, one thing that our first speaker did was sort of define utilization as part of a sort of a pathway of capture, transportation, utilization. What I would tell you is that's not necessarily the case. We'll talk about CarbonFree as an example of where there really is no transportation needed, because the capture and utilization are located at the same spot. So I would say that we always want to be careful about not limiting ourselves and not limiting the way that we think about our technologies. We want to, especially in this time when there is so much development going on, keep a broad open mind about what is possible, because ultimately it's going to take us all to solve these things. The other thing that I would mention briefly about carbon utilization is that it is really distinct from enhanced oil recovery. And you know, as you know, enhanced oil recovery really injects CO2 into oil and gas wells to increase production. What I would tell you is I think that the goals of EOR are different really than the goals of carbon utilization, and the facts around them are also different. So they're really two different conversations. Kind of going on to talk about the circular economy. Now, the circular economy is really sort of a framework for managing carbon emissions using a closed loop system involving the 4 R's, reduce, reuse, recycle, and remove. Okay, examples of carbon utilization helping out this idea of the circular economy include reducing the need for sourcing carbon from oil and gas production. So we're decreasing the amount of natural resource production that is necessary. Reusing carbon dioxide as a raw material, recycling that carbon dioxide into valuable products, and removing carbon dioxide that would otherwise be emitted into the atmosphere. So I think it's perhaps a bit easier to understand what we're talking about with an example. So selfishly, I will use our technology as an example of both utilization and the circular economy. Now, just to give you a very brief overview of our technology, we remove carbon dioxide at a point source emitter, taking, for example, raw flue gas from a steel mill directly into our system to first capture that carbon dioxide. Once that carbon dioxide is captured, we convert it to calcium carbonate. And we also have hydrochloric acid as a byproduct. That calcium carbonate is actually a valuable commodity chemical that is sold. But we recycle that hydrochloric acid back into our system to help produce our feedstocks. One of the things that we can do with that hydrochloric acid is combine it with waste materials like steel slag, which are rich in calcium, to form calcium chloride, which is one of the feedstocks for our process. So we're recycling and reusing the feedstocks from our own process. Now, just as a quick aside, next slide, please. One of the things that people always ask is, okay, why, what is calcium carbonate? Why would anyone want to buy it? What are you guys up to? So calcium carbonate, pretty simply, is a non-hazardous mineral which naturally occurs as limestone, marble, and chalk. Okay? It's used in a variety of different applications as a whitener, a brightener, a scouring agent, a filler, and it can also be used as a nutritional supplement. So, for example, if you had some cereal this morning, there's a good chance that the source of calcium in that cereal was calcium carbonate. Oh, by the way, calcium carbonate is also what Tums are made of. If you had to take any of those last night after some of the spicy tamales. So there's a variety of uses that we have for calcium carbonate. Now, if it occurs naturally, why do we need to produce it? Well, the answer is that it generally doesn't occur naturally in sort of high purity and uniform particle size that is needed for industry. And the existing process that's used to produce it for industry has a very large carbon footprint because it involves both mining limestone and then heating it up to very, very high temperatures in order to essentially burn that limestone down to the pure calcium carbonate. So we're looking at providing an alternative to that current use. Next, please. So let's talk a little bit about the circular economy, because as you get into it, you may find that a lot of technologies have more circular economy impacts than you first might guess. So starting with removal, the obvious thing is we're capturing carbon. So we're helping remove that carbon from being emitted into the atmosphere. But there's a side benefit to our technology. If the emissions that we are capturing include SOx, NOx, and particulate matter, those will also be captured by our technology, with really impacting the quality of the calcium carbonate that we can produce. Reduce. Okay? So carbon-intensive calcium carbonate production can be displaced by our technology. Calcium carbonate mining can be decreased from needing to go on. And fossil fuel ultimately combustion that is involved in those two activities can be reduced. So we can have a broader impact than just the impact that we're having at this one particular site. Reuse. Calcium, of course, is being reclaimed from a waste material, as we talked about in this technology. The other thing that we can do is in flue gas, you'll often find that there is some amount of residual fuel that isn't combusted in the underlying industrial process. So you may find that there is hydrogen, carbon monoxide, or even natural gas that is left over. That can be used in our system because some heat is required. Okay? But then we can run the exhaust from that heat production back through our system to capture that carbon as well. And then finally, recycling. So as I already mentioned, we are reusing that hydrochloric acid that we produce, but in addition, we can regenerate the other feedstock that we use, which is magnesium hydroxide, through our system. So at the end of the day, we can have a very low impact and help clean up things other than just the carbon dioxide by doing things like using waste materials to produce the feedstocks that we need. So final slide. So I want to thank you for taking a few minutes to listen to me talk about carbon utilization. I certainly am thankful for the opportunity to do that. If you're interested in more information about our technology, the QR code to your left is a link to our website. The QR code to our right is a link to my business card. So happy to talk to you more during some of the breakout sessions of the conference. Thank you very much.
Thank you, Brent. Last but not least, we have Meghan Kenny, Director of Strategy and Projects at CarbonCapture Inc. Meghan's going to tell us more about direct air capture. They have a wealth of experience in various roles, including working as a researcher at the MIT Department of Chemical Engineering, a process engineer at Johnson Matthey, and a consultant and manager at Bain & Company. Welcome, Meghan.
So to start, I could tell you a little bit about CarbonCapture Inc. We are a direct air capture technology and project developer. For those not familiar with direct air capture, we make machines that effectively take ambient air, separate out the CO2, and then you can use that concentrated stream to do many different things that we'll talk a little bit about more in the next couple of slides. Next slide, please. This chart will look familiar to a lot of people in the room already, but as a bit of a recap, recent findings from the IPCC and other reputable reports suggest we need to build at least 5 gigatons of annual carbon removal capacity. That's in addition to all of the work being done on carbon reduction in order to stay close to the 1.5 degrees C scenario. Next slide, please. There are several ways to build out this capacity, and realistically, all of them will be necessary at some scale. I'll spend a little bit more time talking about direct air capture today, but generally, these methods can be placed on a scale from more nature-based to engineered solutions. This diagram should not be considered exhaustive. Even within each of these categories, there may be some options that fall in different parts on this spectrum. On the more nature-based end, we have some of the more common and well-known examples of CDR. These include things like forestation and forest management, or soil management techniques. On the more engineer side, we see methods like biomass carbon removal and direct air capture plus storage or utilization. All of the categories have pros and cons that should guide how and where they are deployed. There are a lot of great resources out there, like the CDR primer and work put out probably by many of the people in this room as well, that detail all these different methods and the trade-offs associated with them in the CDR landscape. Next slide, please. To dive a little deeper into the trade-offs for direct air capture specifically, the most common arguments it faces are its energy requirements and unit capital costs. I also want to give credit for this stolen slide. Boston Consulting Group completed this analysis for a report they put out in June that I highly recommend to anyone looking to learn a little bit more about DAC. DAC is an energy-intensive process. We are a company interested in and selling net carbon removal. Subsequently, we need to complete a life cycle assessment, otherwise known as an LCA, that accounts for all of the emissions associated with capturing and storing CO2. All those emissions effectively decrease what can be made available to customers, and more importantly, the net benefit of the project. CCI's technology is just one example, but with most energy sources, energy accounts for over half the emissions associated with our process. This suggests that at the end of the day, DAC can really only be successful by running on low carbon energy sources. We are addressing the energy challenge in two main ways. The first is supporting development of additional low carbon energy generation. I call out additionality specifically because we, as intending to deploy kind of megaton scale projects, do not want to affect the cost, mix, or reliability of energy for anybody else using the same infrastructure. On the other end of the spectrum, we are working to decrease our unit energy requirements through a number of different ways, including through capture material improvements. This is, for example, developing sorbents with a lower desorption temperature, systems approaches, such as reactor design improvements and improving heat recovery, and finally, opportunities for synergies such as waste heat recovery. As an example, we're part of a DOE project now with US Steel utilizing waste heat facility from one of their plants. On the CapEx side, DAC technology is still very much considered first of a kind. Getting down the cost curve outside of some major technological discovery will require regular, repeated deployment of systems that are expensive and may not be very efficient at first. Thankfully, there has been significant support on both the federal and private side to help bridge this gap. For example, the DOE and private funders have released funding opportunities for pilot projects. This is in addition to the huge amount of funding that's been made available for the development of 4 regional direct air capture hubs in the US. The Inflation Reduction Act last year dropped the minimum project size to 1,000 tons per year to qualify for 45Q tax credits. And many corporations have made huge pre-purchase commitments that will allow these projects to scale in the near term. Next slide, please. I'd be remiss if I didn't also stress that direct air capture is just one piece of a much larger puzzle, some of which the first speaker went over. We talked a little bit about low carbon energy, but successfully scaling DAC also requires the development and scale of storage opportunities. We have a few examples here, such as permanent geological storage, low carbon concrete, carbon black, and sustainable fuels. There's a lot happening concurrently in this space, which would require a much longer separate talk. But hopefully that means that DAC will also benefit from support on other parts of the project scope, such as the stacking of tax credits and the proliferation of geological storage options as states are given primacy over Class 6 well approval. And final slide, please. I know that I'm quite biased, but I'm really excited about what the next couple of years have in store for DAC. Thank you for your time. Happy to chat with anyone during the break or answer any questions.